Example number 7. I'm going to try to recognize that this cosecant of negative x is part of my even-odd identity set. Cosecant of negative x is just the negative of cosecant x. So I'm going to replace that right here, this one, with just a negative cosecant regular x. Okay. Now basically I'm just going to try to simplify this left-hand side to be equal to sine and cosine, sine minus cosine over there. So secant is, this one and this one are 1 over cosine, and cosecant is 1 over sine. And on the bottom you have 1 over cosine times 1 over sine. Okay, I'm going to clean this up a little bit. I've got 1 over cosine x minus 1 over sine x in the numerator, and in the denominator I have 1 over cosine x times sine x. So, you know your fractions, all you have to do is multiply by the reciprocal of the denominator. So, I'm going to first actually get the numerator to be one entire fraction instead of 2, and then we can multiply by the reciprocal. So what I'm going to do is I'm going to multiply the first one up here by sine of x over sine of x, and then multiply the second one by cosine of x over cosine of x, because then I get a common denominator. Then I have sine of x over cosine x sine x minus cosine x over sine of x cosine x, and then that gives me sine of x minus cosine x over cosine x sine x. Now all of this is being divided by 1 over cosine x sine x. So now I'm ready finally to multiply by the reciprocal. So I take my numerator, sine of x minus cosine x, over cosine x times sine x. I'm going to multiply by the reciprocal of this, which puts the cosine x sine x on the top of the fraction, and the 1 on the bottom, thereby canceling these two, and we get sine x minus cosine x for just the left-hand side up here. All I've been doing is working with the left-hand side. So now I've turned this whole thing into sine x cosine x, and therefore, if I set that equal to the right-hand side, I'm saying the left side is this, and going back up to the original position, the right side is this. They are exactly the same, and therefore I've proved that they are indeed an identity, that those two things are the same. The last example, what I would do on this one is, again, I would find a common denominator here by adding these two together. So the first one I would multiply by 1 minus sine of theta, and the second one I would multiply by 1 plus sine of theta. Notice I'm doing this on the top and the bottom. So I get this over here. If I FOIL these together, I get 1 minus sine squared theta. And on the other side, I get that same thing, 1 minus sine squared theta, by just FOILing them together. So I can add them together, and what happens is when I add the tops together, the negative sine theta and the positive sine theta cancel, and then 1 plus 1 gives me 2. And then on the other side, I'm going to also factor out a 2 from this tangent function. So it's going to be 2 times 1 plus tangent squared theta. Now it turns out that 1 plus tangent squared theta is the same as secant squared. So I'm going to take 1 plus tangent squared theta out, and I'm going to put secant squared in its place. So I get 2 times secant squared theta. And then down here, 1 minus sine squared theta is also a Pythagorean identity. It's right here. This tells me that this is cosine squared. So over here, I have 2 over cosine squared theta if I replace this here. Now, is that equal to 2 secant squared theta? Yes, it is. If I multiply on both sides by, actually, no, not multiplying on both sides. If I rewrite the left-hand side as, let's see, it's basically 1 over cosine here. And if this was a squared identity, what I could do is say that this is 1 over cosine squared, and that's equal to secant squared. Then I could simply rewrite this one as 2 times 1 over cosine squared, which is 2 times secant squared. And then I finally have them as equals.